33 billion years. That's the estimated time of death of the universe. And the cosmos is already more than 1/3 of the way through to that moment. It was expected to expand forever under the influence of constant vacuum energy. We thought the universe would accelerate infinitely. But new data suggests the opposite. Research points to a change in dark energy. If its pressure continues to weaken, expansion could slow, stop, or even reverse into a final big crunch. This discovery calls everything we thought we knew about the fate of our universe into question. Why 33 billion years? What evidence points to this dramatic outcome? And what does it mean for the cosmos and for us? As you may have guessed, today's journey will explore new research that radically changes the timeline for the end of the universe. And this time, it is not being presented as an unfounded hypothesis. The results of the Dark Energy Survey and the Dark Energy Spectroscopic Instrument indicate that dark energy may be variable, deviating from the constant lambda in the lambda-CDM model. This data reshapes our understanding of the distant future. Not endless acceleration by default, but a trajectory that may slow, stop, and turn in the opposite direction. The implications extend from fundamental physics, fields, particles, and gravity to long-term planning for civilization, mission horizons, windows for intergalactic travel, and how colonization strategies might change if expansion does not last forever. So why does it matter if dark energy is not constant? Let us start with the fact that the universe has not always expanded at its current pace. In fact, after the Big Bang, gravity dominated for billions of years, slowing the initial expansion. For the best part of the 20th century, scientists assumed that this deceleration would continue and might one day bring expansion to a halt. But in 1998, a shocking discovery rewrote that story. Distant stellar explosions known as Type 1A supernovae appeared dimmer than expected. Dimmer, meaning they were farther away than their redshift suggested. The only explanation was astounding. The expansion of the universe was not slowing down. It was speeding up. Picture this. Imagine a car that starts out slowing down but gradually presses harder and harder on the accelerator. Well, gravity was the braking force in the early era. And then later, this invisible engine began to push with more and more force over time, so that the car not only stopped decelerating, but started accelerating. This was the dawn of what we now call dark energy. An unknown force or property of space itself pushes galaxies apart at an ever-increasing rate. Today, it's believed that dark energy makes up about 68% of all energy in space. It's like a negative pressure permeating every corner of space, stretching the fabric of the universe outward. The leading theory anchored in the lambda cold dark matter model, lambda CDM, it states that dark energy is a cosmological constant, fixed, unchanging vacuum energy. In Einstein's equation, this constant lambda offers a simple and elegant explanation for accelerated expansion. A constant repelling pressure that becomes increasingly dominant as the universe expands. According to this model, the future seemed fairly predictable. If dark energy were truly constant, expansion would continue infinitely. Over trillions of years, galaxies not bound together by gravity would disappear from view. Stars would exhaust their fuel, matter would decay, and the cosmos would sink into a cold, dark heat death. This was the Big Freeze scenario: gradual cooling to complete extinction. The only alternative at the time was an even more extreme Big Rip, a scenario in which dark energy somehow grows stronger over time. In any case, a Big Crunch, the future where the universe collapses back in on itself, seemed unlikely after 1998. Gravity simply lacked the strength, leaving dark energy firmly in control. At least that's what we believed. However, scientists never stopped asking questions. Could dark energy be more complex than a simple constant? Some hypothesized that it could evolve or change, a concept known as quintessence, in which dark energy is a dynamic field rather than a fixed value. Others even wondered whether our understanding of gravity itself might be incomplete. These ideas remained speculative. They were nothing more than intriguing thought experiments without sufficient supporting evidence. Until now. Since then, our technology has advanced. Specifically, over the past decade, 2 ambitious projects have been carried out to create an unprecedentedly detailed map of the cosmos. The Dark Energy Survey, or DES, scanned the southern sky, cataloging distant supernovae and the distribution of galaxies and galaxy clusters. Meanwhile, the ongoing Dark Energy Spectroscopic Instrument, or DESI project, is measuring the exact distances and velocities of millions of galaxies, creating a vast three-dimensional map of the universe. By charting how the universe's expansion has unfolded over time, these studies aim to determine whether dark energy is truly constant or if it has changed. The first results have been intriguing. Over the past year, DES and DESI data have begun to indicate that the influence of dark energy may be changing. Subtle patterns in galaxy clusters and in the brightness of distant supernovae suggest that the universe's acceleration does not perfectly match a constant lambda. In fact, the data, preliminary but statistically significant, indicate that the dark energy may have been stronger in the past and is now slightly weaker than the lambda CDM model predicts. If this is true, it contradicts the standard cosmological model, which assumes unchanging dark energy. Realizing that there might be something else happening, theorists took action. Could there be an explanation for the weakening of dark energy? One bold proposal published in mid-2025 suggests that dark energy may be two-faced. In this new model, dark energy is not a single entity. It is a combination of 2 components. The first is an ultralight particle called the axion, a hypothetical ghost-like particle that drifts through space with almost no interaction. If they truly exist, axions form a pervasive field stretching across the universe. Their combined energy, although incredibly weak, could explain the accelerated expansion we observe today. In essence, the axion field acts like a kind of fuel for expansion, pushing galaxies apart. The second component is none other than Einstein's cosmological constant lambda, but with a peculiar characteristic. In this model, lambda is not the dominant force. In a surprising twist, it may even be negative. At present, the positive energy of the axion field outweighs this small negative lambda, creating a net push that accelerates expansion. If this is the case, current acceleration of the universe is a temporary phase powered by axions. However, this won't last forever. As the universe expands and ages, the axion field is predicted to thin out. Its energy density will gradually decrease and lose steam. In other words, if this is true, we may have our first scientific explanation not only for why the universe could expand, but why it could one day collapse. When the axions are weak enough, the negative cosmological constant lurking in the background will finally take over. Unlike a positive lambda that pushes space outward, a negative one works in the opposite direction. It acts like a cosmic tether, slowing the expansion of space rather than speeding it up. At first, this change will be imperceptible, a gradual slowing of expansion. Eventually, the repulsive force of dark energy will vanish entirely, and the pull of gravity, now facing no resistance and even reinforced by negative vacuum pressure, will dominate. Expansion will slow, stop, and then reverse. According to the authors of this model, in cosmic terms, the reversal could begin surprisingly soon. They estimate that the universe's expansion could start slowing in just 10 billion years, which is less than the current age of the universe. The beginning of the end, as they call it, will mark the moment when galaxies that have been drifting apart for eons will gradually start to come closer together. What will follow is a slow collision on a grand scale. For the next 10 billion years, the cosmos will contract in a long twilight collapse. Galaxies will merge into even larger structures. Distant galaxy clusters will rapidly draw nearer to one another, and the future observers will witness a night sky completely transformed. As contraction accelerates, the universe will shrink. Matter will heat under pressure. Over billions of years, the universe as we know it, galaxies, stars, planets, will close in. In the final moments, all the matter and energy of the cosmos will be compressed into an ever smaller volume. Temperatures will rise sharply. Atomic bonds will break. Stars will collide, and black holes will merge. Eventually, the universe will end as a fireball of unimaginable density and temperature, essentially becoming a new singularity, the mirror image of the Big Bang. That is the Big Crunch. If our calculations are correct, the total lifespan of our universe will be only 33 billion years, and we are already 1/3 of the way to the end. It's important to note that this is still only a hypothesis. The DESI and DESI results that inspired it are preliminary for now, and they are only statistical assumptions that require confirmation. The axion model is one way to interpret the findings, but it is not the only idea under discourse. Another theory gaining traction in some ways, and even more striking, what if the universe is not as uniform as we think? What if, on the largest scale, it has a slight spin? In mid-2025, physicist Nikodem Poplawski pointed to intriguing evidence that our universe might be rotating. Data from powerful observatories, including the James Webb Space Telescope, reveal a surprising pattern. and observed a symmetry in the rotation of galaxies. Deep field studies show that roughly 2/3 of examined galaxies appear to rotate in the same general direction rather than at random. Moreover, the spin axes of these galaxies and motions of galaxy clusters exhibit unusual alignment. It's as if the universe has a subtle but clear axis, a preferred direction in the cosmic arena. If this is true, this would be major news. Since Copernicus, we've assumed that the universe has no special orientation or center. This is the premise of the cosmological principle. A rotating universe breaks that assumption. Yet Poplawski says that such rotation could answer some of our deepest cosmic mysteries. It would be amazing if a simple rotation of the universe was the origin of dark energy, he reflects, especially since it predicts its weakening. How would a rotating universe be able to mimic dark energy? This idea relies on centrifugal force, the same effect that pushes people outward on a merry-go-round. In a universe with a slight rotation, on the vast scales beyond galaxy clusters, that rotation could impart a small outward acceleration to matter. Poplawski suggests that what we call dark energy might actually be the result of this cosmic spin, a kind of inertial push that drives galaxies apart. Crucially, if the universe is closed, meaning it is finite in volume and rotating as his model proposes, then as space expands, the rotation slows down. Kind of like a figure skater slowing their spin by extending their arms. And here is the most fascinating part. As cosmic rotation slows, the outward centrifugal force also decreases. In other words, the effect of dark energy would gradually weaken over time. Now that's an intriguing coincidence, given that DESI observations point toward a dark energy decrease of this exact nature. Poplawski's rotating universe concept is closely tied to another bold idea: black hole cosmology. He proposes that our universe may have been born out of a black hole into a parent universe. To take this concept further would suggest that every black hole could be a gateway producing a new baby universe beyond its event horizon. In this scenario, the rotation of the parent black hole is inherited by the baby universe it creates. And so the preferred axis of our universe might simply be the spin axis of the black hole where our universe formed. Now, this is a wild and captivating concept which, if true, would mean that our universe exists within a cosmic family tree of universes, a multiverse connected through black holes. Rotation offers a natural explanation for dark energy, and the multiverse provides a reference frame for that rotation beyond our own universe. Does this mean that our universe will eventually stop expanding and collapse? The rotating universe model, as it stands, does not guarantee the Big Crunch. Its main achievement is to show how the observed weakening of dark energy could be explained without exotic new particles, but purely through geometry and motion. However, if dark energy generated by rotation continues to fade, it's possible this too could lead to slowing expansion. A rotating, closed universe might reach a maximum size and then, depending on its total mass and energy, possibly contract. The Axion dark energy model and the rotating universe hypothesis both attempt to interpret the clues we observe. They present very different visions. One, adds a new ingredient to the recipe that makes up our cosmos: axioms plus a twist in lambda, while the other rewrites the very architecture of space. And yet they share a common thread: the idea that dark energy might not be a simple, unchanging force after all. It could merely be a phase in the universe's history, one that changes and eventually comes to an end. And if that's true, the long-term future of the cosmos could be radically different from the endless expansion we once imagined. The implications of a finite lifespan for the universe are profound. For over 2 decades, lambda CDM with its constant positive cosmological constant has been the foundation of cosmology. If dark energy truly evolves, this foundation will need reinforcement or revision. From a scientific perspective, confirming changes in dark energy would force theorists to urgently update our fundamental models. It might be an ultralight axion field interacting with gravity, or a modification of general relativity itself, or some other yet unknown quintessence field. A negative lambda, if confirmed, would mean that in the long run, our universe resembles an anti-de Sitter space, a geometry with a natural tendency toward contraction, beloved in theoretical physics, for example in string theory, but previously thought irrelevant to our real cosmos. This could open possible links between cosmology and quantum gravity, as physicists still struggle to understand how vacuum energy could be below zero. And then there's this existential angle. We humans live in a universe that may already be in its middle age. Sure, 33 billion years is almost unimaginably long, far beyond the lifespan of our Sun, Earth, or even our galaxy in its current form. But in principle, a finite lifetime for the universe means there's a cosmic deadline. This matters for space exploration and colonization, even if on timescales that dwarf human history. Many futurists imagine that life, if it endures long enough, might spread to other galaxies over trillions of years. In an eternally expanding universe, distant colonies would eventually become isolated, as accelerating expansion outpaces even the fastest spacecraft. But in a universe that reconverges, far-flung journeys could one day be aided by the cosmos itself. This is speculative, of course, yet understanding the universe's long-term structure could be a turning point for such grand ideas. Before getting carried away, it's worth emphasizing once more that the arguments for a big crunch are based on data that are still coming in. DES and DESI results require verification. Upcoming missions will be critical. Euclid, the European Space Agency's space telescope launched in 2023, is already surveying billions of galaxies, up to 10 billion light-years away, mapping how dark energy's influence has changed over cosmic history. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will refine our measurements of cosmic expansion with extreme precision. These observatories, together with ground-based projects like the Vera Rubin Observatory, will either confirm or disprove the subtle trends being observed right now. Within the next couple of decades, we'll know whether the strength of dark energy is truly declining, and if so, how fast. The fate of the universe could shift from an eternal philosophical question to a solvable scientific problem with a data-driven answer. We begin with a simple, staggering possibility that our universe has an expiration date, 33 billion years from its conception. We have now seen how this idea rose from the faintest hints, small anomalies in the way galaxies cluster, and how light travels across billions of light years. We've always looked up at the stars, wondering about eternity. Now we must consider that eternity itself might be shorter than we thought. And if all the answers point toward an ending, they also prompt a new question. Could anything be done to change the outcome? Could intelligence, however advanced, find a way to survive the cosmos that gave rise to it? Could future beings somehow escape the collapse of our universe, perhaps by leaping into a neighboring multiverse or creating universes of their own? Or is the final singularity an unavoidable boundary, the ultimate horizon beyond which nothing exists? We do not have the answers, but the countdown to the big crunch has already begun.